Vincent from Taiwan, reporting problem number 9, oscillating screw. This is a problem statement. When placed on the side on the ramp and release, a screw may experience growing oscillation as it travels on the ramp. Investigate the motion and also the growth of these oscillation. According to our problem statement, we mainly focus on these key points, including a critical condition and also the reason for growing oscillation, and some key parameters determine the phenomenon. This is the observation. First of all, this is our experimental setup, which we use a ramp whose length is about 1 meter, and we use an adjustable table to control the incline angle delta of the ramp. Then we set the camera parallel to the ramp in order to record a motion and set the ramp as the XY plane. Then we design a camera track and also a camera holder that can slide on it in order to record a motion closely, and also record the details in the oscillation. This is a demonstration of a trajectory of a screw. So in the video, you can see that the screw will slide down as it travels down a ramp. And we plot it to a spatial trajectory of the screw. Then we set the ramp as the XY plane, then we can get the graph at the right side. So if we gradually increase the incline angle delta, we may see the vertical displacement between each oscillation increase. Then this is the analysis of a swing of screw and oscillation. First of all, we define the oscillating angle phi as the included angle between the screw and the vertical axis. Then in the graph, we vary the releasing angle. Then we observe the phenomenon of growing oscillation by investigating the peaks of the oscillating angle. So when the releasing angle increases, the phenomenon becomes more significant with bigger growth and also bigger oscillating angle. And we can also see the oscillation in the trajectory of the screw. Then this is the explanation. This is the qualitative explanation. So first of all, the screw will slide down because of the tangential velocity difference between the head and the tail of the screw. However, it won't stay at the equilibrium point because of the inertia. Then the gravitational component is bigger when the oscillating angle phi is bigger. Then in this part, we can separate the energy into 3 parts: kinetic energy, potential energy, and the energy friction consumes. If the transiting energy, which means the potential energy transits to kinetic energy, is bigger than the energy consumption by friction, the screw will experience growing oscillation, which is a phenomenon we are going to investigate. Then this is our theory. First of all, in order to derive the equation of motion, we consider all the forces acting on the screw, including the forces acting on the 2 contact points, which are friction and normal force, and also the gravitational component acting on the center of the mass on the y-axis. Then we can obtain the value of the acceleration in the x and y-axis. Then by calculating the momentum, including 2 oscillation, include the self-rotation and also the oscillation of the angle phi. And by taking its differentiate, we can get the value of angular acceleration by crossing the moment's arm to the forces acting on the 2 contact points. Then in order to find a normal force, we have 2 constraints here that restrict the screw to always contacting the ramp. So by using these 2 constraints, we can get the value of normal force. Then we can notice that normal force will not be constant throughout the oscillation, and then the friction will not be constant throughout the oscillation. And we mentioned the energy transform in our qualitative explanation. So in this part, we analyze the dissipative force by using the experimental data that the blue one is the potential energy loss and the orange one is the translational energy, and also the rotational energy, which is the green one. And by subtracting them, we can get the energy dissipation, which is the black area of the arrow. Then if we plot the energy loss and compare it with our theory, it's matched really well with our theory, which can prove that all of the dissipation is from kinetic friction, and we have already considered all of the dissipation. Then by analyzing the energy loss for the head and the tail, we can find out that for the head, it has a bigger energy loss because of a bigger normal force acting on it. Then we analyze the region for growing oscillation. We separate the phenomenon into 3 stages: growing oscillation, decaying oscillation, and stopping. Stopping means the screw stops in the middle of the ramp, and we have an example of decaying oscillation and also growing oscillation in the right graph. So you can find out that the growing oscillation happens when the inclined angle and the releasing angle is big enough. Then by increasing the friction coefficient, which means the dissipation increase, we may notice that the boundary shift right, which means that we need more inclined angle and releasing angle for a screw to experience growing oscillation. Then in order to fully analyze the phenomenon, we also consider and also analyze the spinning angle, which is the self-rotating of the screw, which is the angle psi. And by comparing to our trajectory of the screw, we found out that when the screw oscillates to the turning point, it reaches the maximum angle of phi, and the self-rotation velocity is close to 0, which means that when it reaches turning point, the screw is start to turn to other direction, including the angle phi and also the angle psi. Then this is our experiment about the growing oscillation. The first experiment we did is about varying the releasing angle. First of all, in the left graph, we may notice that the blue one is the first oscillation, first peaks of the oscillation in the right graph, and the orange one is the second, and so on and so forth. Then for example, for releasing angle at 30 degrees, the vertical one is the 3 oscillation of one motion with the releasing angle is 30 degrees. Then you can notice that with a bigger releasing angle, both the oscillating angle and the growth of the oscillation increase, which means that the phenomenon became more significant. The reason for that is actually because of the vertical displacement between each oscillation. So we explain it by, so we plot the vertical distance between the initial to the first turning point. We find out that when the releasing angle increased, the vertical displacement is increased, and it also have a great agreement with our theory. So it means that the potential energy loss increased within each oscillation. Then the second parameter is the inclined angle delta. So in this situation, we find out that when the inclined angle increase, the potential energy change will increase, which causes a growth increase and also the oscillating angle increase. Then interestingly, we found out that there's a contact point between these 4 theory lines, and this is actually a boundary condition we mentioned previously. So below 11.3 degrees, the screw will experience decaying oscillation, and it also have a great agreement with our experimental data and the theory. And corresponding to our investigation about region for growing oscillation, it's matched really well with our theory. And here are some more parameters affecting the screw's motion. The third parameter is the friction coefficient, which we change 3 kinds of material in this part. So when the friction coefficient increase, the torque of friction increase, which increase the energy dissipation from friction. So the growth and also the oscillating angle decrease. And there's also a boundary condition in this part, which is a black line. Then interestingly, we find out that there's a yellow region in this part between 0.275 and 0.293. In this region, we may see a growing oscillation after several decreasing happens. Then the last parameter we conduct is the screw length. When the length of a screw increase, the rotational inertia increase, which caused the phenomenon became less significant. So in this part, we also analyze the oscillating period. We found out that the oscillating period decreased when the length of the screw decreased, and we define it as the time difference between the maximum oscillating angle. However, we may notice that there is a big deviation with the smaller length of the screw, for example 1.6 centimeter. And we believe this is the influence of the thread. So we analyze the structure closely. So we notice that with a shorter length, the structure of the thread is actually non-symmetry. So it will cause the variation of the angle alpha, and with a shorter length, the variation became bigger. So for example, in the left graph, when the angle of alpha increased, the oscillating angle increased, and the oscillating period decreased. Then by using this modification, for example, we use the average of alpha for 6.4 degrees for 1.6 centimeter. And the deviation became much more smaller, both in the peaks of the oscillating angle and also the oscillating period. And the trend fits match very well with our theory, with our experiments. Then this is the conclusion of a report. So first, why does a screw oscillate and experience growing oscillation? The screw will oscillate because of the tangential velocity difference between the head and the tail of the screw, which causes the screw to oscillate down. And also, we plot the energy loss in between our experiment and also our theory. And we can prove that all the dissipation is from kinetic friction. So we are able to derive our theory by considering the kinetic friction acting on the screw and also all the forces and also the torque acting on the screw. So by comparing with our theory and our experimental data, you can see in the right graph that it has a very great agreement between our theory and experiments. Then second, in which situation will a screw experience growing oscillation? We found out that there's a boundary for the screw to experience growing oscillation, which the inclined angle and the releasing angle need to be big enough. And by increasing the friction coefficient, the boundary also shifts right, which means we need more inclined angle and releasing angle for a screw to experience growing oscillation. Then from the perspective of the energy, the growing oscillation happens when the transiting energy is bigger than the energy consumption, which is a black area in the energy transform part in the right graph. That dissipation is from, all of the dissipation is from kinetic friction. And this is the end of a report from Team Taiwan. Thank you.
So questions by the opposing team?
Okay, thank you, reporter, for the insightful report. Firstly, how do you get your kinetic friction coefficient?
We actually measure that we vary the inclined angle here, that when the inclined angle is big enough for a screw to slide down, and we substitute the relevant variables into this equation, which is a kinetic friction measurement.
Thank you. Okay, so you assume that your kinetic friction coefficient is the same as your static friction coefficient?
Sorry.
No, okay, never mind, sorry. No, it's okay. So you assume no rolling friction and air resistance in your theory, right?
Yes, because we plot the energy loss and it has great agreement, so we believe all of the kinetic friction. Okay.
You can go to slide 14.
14.
How do you get your spin angle of the screw experimented?
We actually draw some dots on the on the body of a screw. Okay.
Okay, thanks. Okay, if you go to slide 11.
11.
How do you get ds for the tail and the head?
And this is obtained by the experimental data, which we track the head and the tail of a screw to get the displacement.
Okay, so this is when you're just sliding down the ramp, right?
Sorry.
Like this is when you're just sliding down without rotating, right?
No, this is oscillating. This is a phenomenon in the. Yes.
Okay, thanks. Okay, for slide 26.
26. This one.
How do you get your experimental graph for the friction dissipation?
For friction dissipation, we subtract the potential energy loss and subtracting the translational energy and also rotational energy, and the difference
how
between.
How do you get the error bars for your graph on the left?
And we actually did a very a great amount of experiments. That's we did 10 times for each point, so we get the error bar.
Thank you.
Thank you. 5 minutes preparation time for good.
How? I agree.
如果偶尔才好。
为我不小心用到那个蛋糕。
哦，原来。
By comparing the energy loss, we can prove that all of the dissipation is perpendicular to LSS.
第二个问题是问你说你的 static 跟它的那个值是怎么样，然后
这是什么问题？
我不知道他，我听起来是这样。
我感觉他自己也没有很确定他会说。这个英文，好了，还可以理解。
不然他就是问你两个取得的方式是怎么样。
哦。
那个是你怎么 get 你的data？
我那个有顶吗？直接修出后面那个。
有，OK 还好。那我比较期待你那个相机那个自转拍自转的那个。
好。
需要那个拍自转。
对不起。
那个修出来也是。
然后他等下在讨论到自转，就直接修这个。
For fiction 的时候，我觉得其实不是 all of the dissipation，就是
most of the dissipation 好。Computation。直接放一个大的。
我们要准备手写板。
他手写。
新加坡。
对。
新加坡都是手写强度。
没关系，我刚刚画。
你网路现在是连自己还是有线？
啊？
你网路是连这里还是有线？
连这里。
好。
忘记接有线。有没差？这样。
就这点而已，不然跑分线，我画了两次关。As the phenomenon descends into the initial condition, conduct experiments for various steps.
我刚刚问那个问的对我很好。好吧。Or 10 times。不要 10 times。
你这个做了多少？
啊，我写。其实就是5次。没有啊，其实大部分都5次，是那个是确实是10次，只是他刚好问到10次的图片，我觉得10次。
刚好那个点10次。
没有，他刚好问到那张，因为这超好做的、啊，这个方日语。我那天不是一直在那边画画。前面这些图都是5次。这样我应该直接是这个 PPT 吧，应该直接是 PPT 吧，因为不用投这个东西。
So you should start share your screen. Only 10 seconds left.
Theory proof it's our
那个最后我讲的。
那个 test 我跟你介绍fully.
Okay. Hello everyone, I'm Luke Mazaru from Team Singapore and I'll be opposing problem number 9, oscillating screw. So in summary of the reporter has first qualitatively explained the increase in kinetic energy during the motion of the screw, which results in the growth of oscillations. He has also quantitatively modeled this phenomenon using the Newton's second law as well as the torque equations, and he has experimentally varied the release angle, inclination angle, friction coefficients, as well as the length of the screw, and investigated how they affect the motion. Now I will cover some strengths and areas for improvement of this report. Firstly, he has produced the phase plots for the growing oscillations, and this has clearly demonstrated the parameters resulting in the growth. For example, he has varied the friction coefficient and showed that it increases the required ramp angle for the screws to begin oscillating. Furthermore, he has quite a good quantitative overview using both Newton's second law and the torque equation to model this phenomenon. And he has also considered that both contact points are slipping. Furthermore, he has experimentally investigated many parameters such as the inclination angle, release angle, screw length, and the friction coefficients. And I believe that this is quite commendable, as it allows us to have a greater qualitative understanding of how these different parameters affect the phenomenon. The reporter has also characterized his kinetic friction, and since this is a major driving force behind the phenomenon, it is quite important that he does this. And lastly, he has quite a good experimental control, for example, placing his camera on the track in order to reduce parallax error, as well as using a protractor to accurately measure the angle of the screw, the angle of the ramp. However, I do believe that there are some areas for improvement. Firstly, the reporter has quite a poor qualitative explanation of this phenomenon, as he has used the torque from gravity to explain the growth of the oscillations. I believe that this is only applicable if the smaller contact point is fixed, and if the smaller contact point is moving, we can no longer take talk about this point as it is accelerating. As such, I believe that in his qualitative explanation, he should consider the directions of the contact velocities and kinetic friction as the screw slides down the ramp. Furthermore, he also has a contradictory proof to the significance of rolling friction, as he has mentioned that his screw was oscillating during his characterization of kinetic friction, but his graph showed that rotational kinetic energy was not included, and he only showed the potential energy from gravity. Furthermore, he did not model the stick-state transitions at the start of the phenomenon, and since he starts the screw off with no initial angular velocity or translational velocity, I believe that the screw would start off initially sticking. Both contacts would initially be sticking, and it would be invalid to assume that the screw was initially double sticking at the start. The motion at the start of the phenomenon would then be affected, thus changing the initial conditions at which the screw entered the double slipping regime, and this would affect the initial period, the initial oscillation of the screw and affect its amplitude too. I believe that the reporter had also quite a poor experimental control, as his screw was released by hand, and this might introduce some initial angular velocity or spin to the screw, which was unable to account for in his theoretical model, which might also affect the amplitude of the oscillations after the initial release, which might also cause the large error bars that we have observed. He has also substituted the average angle that the screw makes with the vertical when considering the threads. And firstly, I believe that this average angle might not be that applicable, as the screw might spend more time in, for example, a lower angle with the ramp, and he should have tried to see how his theoretical model would predict this motion. And I believe that there is also an additional degree of freedom introduced when he accounts for the thread in this screw, as the screw is no longer maintaining a constant angle with the ramp and instead can oscillate in another plane. Lastly, the reporter had very little discussion into overturn of the screw, which is when the screw does a full 360-degree revolution instead of oscillating about the downwards point on the ramp. And I believe that some interesting behavior would be observed in this regime of motion. So now I would like to invite the reporter up for a discussion. So you your slides. Yeah, thanks. Okay. So for my first point, I would like to discuss the qualitative origin of the growth of oscillations.
Okay, do you mean
so in your
this
report
slide?
you have
This slide.
yeah.
Okay.
Yeah, so in this slide, mg sine beta sine phi would be assuming that your smaller contact point is fixed, right? And this is taking the top about this.
What do you mean by the smaller contact point is fixed? Do you mean the contact point of the tail?
Yeah, the
Oh
smaller
no,
contact.
it is actually not fixed in our assumption.
Okay, so what does mg sine beta sine phi mean in this case?
And I just want to show the gravitational component acting.
Okay, so in this case, what would be the major, since the gravitational component acts about the center of mass of the screw, it wouldn't be exerting a torque on the screw, right?
Yes, and we actually explained the screw to oscillate down because of tangential velocity difference. Since we know that the radius of the head is bigger than the radius of the tail, and it actually has a great difference. So it will generate a tangential velocity difference between the two contact points.
So you believe that the rotation of the screw causes a difference in the contact velocity of the 2 points, which then causes the screw to grow in oscillation?
I believe a tangential velocity difference causes the screw to oscillate now.
Okay, so so as the screw oscillates, why does this difference in tangential velocity cause the oscillations to grow instead of, for example, decaying? Like, could you possibly draw the force of the contact velocities at different points in the motion?
But I cannot draw it. Can I have the whiteboard or something to draw?
If you stop sharing your screen, you'll be able to open the whiteboard.
Oh, I think if you go into presenter mode, you can draw with your mouse also.
Can you see that? Can you see my mouse?
Yeah, you can see that, yes.
Yeah, so actually, like by investigating the gravitational components acting tangential to the body of the screw, like in this part.
So could you draw the contact ball?
Sorry.
Yeah.
The contact what? I cannot hear.
Oh, I think he's frozen. Not sure.
Sorry.
We pause the time.
Can you rephrase that question? Can you rephrase the previous question? Sorry.
打掉，白痴！早叫你第一个先。
可是网上
对，网络打掉。
Are you ready?
I'm sorry. We can start here.
Okay. Sorry, I think you cut out just now. Could you repeat your explanation? Yeah.
So actually, in a different oscillating angle, like this gravitational component acting tangential to the body will, like for a smaller oscillating angle, the value of sine phi will be smaller. So actually, when the screw slides to the top of each oscillation, the gravitational components will increase, which causes the screw to slide in the other direction when it's reached a balance between. Yes.
Okay. I don't think that this will actually cause a growth of the oscillations, because if you consider just a normal pendulum.
Do you mean the growth of the oscillation?
Yeah, so if I think to consider the growth of the oscillations, you actually need to consider both the contact velocities and the kinetic friction forces. And you might get that since the screw is rotating as you go along, the head of the screw, since the head of the screw has a greater radius, the angular velocity of the screw is more important now. Yeah. And then you might get the friction point in different directions.
Yes, I agree with that. Yes.
Okay, then I would like to move on to my next point. So if you go to slide 14 in your slides. Okay, I noticed that for your second oscillation, your maximum for the phi dot and psi dot seem to occur at different times. So do you believe that this might be important to the growth of your oscillations?
And do you mean the maximum of this and this one and this one?
Yes. So they seem to be offset each other.
No, I think the maximum should be at the same time. It's just caused by the experimental error, since this is our video of cell rotation, and we check the body of the screw, and it's the small experimental error is actually caused by because we use the check to closely record motion. However, we cannot fully compare the times and the trajectory well.
I actually don't think that this might be caused by experimental error, and I think that the difference in times of the maximums might actually be also observed in your theory if you were able to plot the graphs. And I think that this difference in times indicates that your spin of the screw, your screw actually continues to spin even after your phi reaches a maximum.
No, I believe that the screw reach a turning point. It will reach a maximum angle of phi, and also the self rotation will stop. I believe it's
that your screw might continue to spin after it reaches its maximum angle of phi, and that might be the reason why it's kind of propelled up even more.
However, you can see this. You can see a phenomenon in our experiments that when it reached a turning point, the screw didn't, like in this part, the screw didn't self-rotate on turning point. So I believe this is obtained by our experimental data and it should be correct. Thank you.
Sure. I think that you should have also tried to theoretically verify this, but I think we'd like to agree to disagree and move on from this point.
Okay.
So now could we go to your graph where you prove that kinetic friction is the major source of damping in your system?
Do you mean this graph?
Yeah, so over here the green line on the left graph is your rotational energy, right? But you have said that your screw is oscillating when you characterize the kinetic friction. So why is the rotational energy zero?
Oh no, we actually consider both the self-rotation and the oscillating angle of phi. They are both considered in the rotational energy in this part.
Yeah, so why is your rotational energy so little compared to
And
your
it's because of
rotational-
the structure of the screw. Since screw is very small, so the rotational inertia is very small, and it's cause the rotational energy is very small in this chart.
Okay, but could I not say that your rotational energy should be approximately of the same order as your translational energy if I was to assume that the screw was at the very start of the motion, since the screw would not be moving very, very fast.
Sorry, did you mean the rotational energy should be closer to the translational energy?
Yeah, so like if you
No, I disagree with this part since we calculate we need to times rotational inertia in our theory, and in our experiments.
Okay, but at the very
So
start
we expect
of
to see the rotational energy should be very small because of the influence of rotational inertia, and we actually calculate rotational inertia and by using this. If you want to mention this part.
Okay, so you have used these moments of inertia to calculate both your rotational energy and the kinetic energy of your screw when it's moving down the ramp. Is that right?
In this chart, it is obtained by experimental data. However, we expect, and it is same as our expectation, since the rotational inertia is small.
Yeah, okay. Okay, so now did you use this graph to characterize your kinetic friction, or was your kinetic friction obtained from a separate experiment?
No, our kinetic friction coefficient is obtained by this experiment.
Okay, then I believe that we agree that your rotational kinetic energy will be quite insignificant as compared to your translational kinetic energy, and that kinetic friction is the main source of damping, source of damping in your system. Okay.
Yes.
So now I'd like to move on to my next point. So if you go to slide 18.
This one?
Yes. Have you investigated how this critical angle changes with different parameters? For example, kinetic friction.
Oh yes, it's actually like this graph, and you can see that the red graph is friction coefficient equal to 0.25, and the original one, which is a black line, is friction coefficient equal to 0.22. And when we increase the friction coefficient, the boundary will shift right because of the increase of the energy dissipation. So we need more inclined angle and releasing angle for a screw to experience growing oscillation.
So could you go back to go back to slide 18?
18, okay.
But you are plotting your graph against your initial inclined angle, right?
Oh yes, so
I think that for different release angles, so for the exact same release angle, you get these graphs at different angles of
no, in this condition, we control a releasing angle of 90 degrees, and then we find out that the boundary is at 11.3 degree of the inclined angle. And comparing to this graph, we may see that the releasing angle here 90 degree, and it's corresponding to the inclined angle of 11.3 degree. So it's matched.
Okay, I understand now. So you're saying that to the right of this point, you will observe growing oscillations, and to the left, you observe decaying as is observed in the graph.
Yes, and so in the green region is decaying, and the blue region is growing, and also in this part, yes.
Okay. Okay, I'd like to move on to my last point now. So you have observed that oscillations can grow after they begin decaying, right?
No, what I mentioned is like this one, the orange one is the second one, and the blue one is the first one. And the second one is actually smaller than the first one, and it grows after. And this is interesting since we observed that a growing oscillation may happen after several decreasing happens.
Okay, thank you.
Okay, thank you. The time is over. The opponent summarizes the discussion.
Okay. So in summary of the discussion, we have first discussed the qualitative origin of the group of the oscillations. And I believe that for this, the reporter used gravity as a top to explain the generation of the difference in the tangential velocities of the head and tail. But I do not agree with him on this point, as I believe that the contact velocities are very important, and we have to consider the kinetic friction factors on both contact points to generate a top rotating the screw. The reporter also believes that the angular velocity psi will be 0 when your phi dot is also 0. But I believe that this is not true, as you might observe a lag between the two, causing your screw to continue rotating even after it has reached its maximum. The rotational energy at 0 in the point. We have also discussed the rotational energy being 0 when you are characterizing its kinetic friction, and we have agreed that both are small. And finally, we have discussed the critical angle for oscillations to grow, and we have agreed that this arises from the space plot, and to the right of this oscillation will grow, and below it will decay. Therefore, I believe that the reporter has quite sufficiently answered the problem statement, as he has investigated many relevant parameters and obtained good agreement between theory and experiment. Thank you.
Thank you. Hadi Lan needs scripture rights and then concluding remarks.
And this is a concluding remark for a reporter. First of all, by comparing the energy loss, we can prove that most of the dissipation is from kinetic friction. And in the opponent's report, he mentioned that we use hands for releasing, and I want to This is the closing remark for the reporter. So first of all, by comparing to energy loss, we can prove that most of the dissipation is from kinetic friction. And also, in the opponent's report, he mentioned that we use hands to release a screw. However, I want to clarify that we use electromagnet to release a screw well. And also, we analyze the structure of a screw well, since we consider the body and the head and the thickness and also the thread. All of the structure has been considered. And we consider different normal force on different contact points and enable the theory to well predict the trajectory. And also, the opponents mentioned that he believed at the turning point the screw will self-rotate. However, we show very clearly in our experimental video that at the turning point the screw didn't self-rotate in our experiment. So it has agreement with our experimental data. Then, as the phenomenon is sensitive to our initial condition, we conduct experiments 10 times each for accuracy. And this is a closing remark for the reporter. Thank you.
Thank you very much. So, questions from the jury? Who wants to start? Okay, Stefan. Sorry?
Yeah, I can proceed. I have a question to the reporter concerning how you conducted the experiment. So as I understand, you used the wooden surface to let you to move your screw on it. I'm just curious whether the surface of this plate is uniform, and could you control how the different parts of the screw